In this video, I will go through the modeling of system in the frequency domain using the impedance method, specifically for mechanical rotational systems. So for rotational mechanical system, for a 2-degree of freedom system, this particular set of formula is used in order to write the equations of motion using the impedance method. So let's say for this particular example, and this example is the same as the example that has been discussed in class. So let's say, for example, we have this particular rod, okay, and this rod is connected to two bearings. So we have bearing D1 and D2, okay, and for this particular system, it can be approximated as shown in figure B, where this particular rod is approximated as having two initial bodies, J1 and J2, and connecting J1 and J2 is a torsional spring with a spring constant K, and at the end of at the both end of the rod we have two dampers, damper D1 with a coefficient of D1, and also another damper at the other end with a damping coefficient of D2. So for this particular example, let's say we are asked to find the transfer function g of s, where g of s is basically theta 2 of s, where the input is t of s. Okay, so that is the problem, and the answer is given in figure C. So let's say we want to try and derive the transfer function for this particular system. So again, we will start with the schematic. So this is schematic B, and for a 2-degree of freedom system, remember that we have to do two schematic diagrams, so one for J1 and one for J2. Okay, let's start with J1. So for figure A is the showing all of the torque and also the impedances acting on J1 only due to the motion of J1. So assume that only J1 is rotating and J2 is stationary, not moving. And what would be the schematic, the resulting schematic? So let's figure it out. So assume that positive theta1 direction is in the clockwise direction. So if we refer to figure B, it is as if you are looking from the right to the left. Okay, so that is the positive theta1 direction. So the first component in this schematic is the torque, the input torque, capital T of S. So if you can see here, capital T of T is in the same direction as theta1 as defined. So we have that. And due to the input torque, we would see the impedance acting on J1. So first we have the impedance from the initial factor J1. So that is given by J1 S squared theta1 of S. We would also see the impedance from the damper D1. So the impedance is given by D1 S theta1 of S. And finally, we would also see the impedance from the torsional spring. The impedance is given by K theta1 of S. So that is figure A. So for figure B, again, assume that only J2 is moving. Now J2 is moving, but J1 is stationary. So what would be the impedance or torque acting on J1 only due to motion of J2? So with the same positive theta1 direction. Okay, so try to imagine in our head J2 moving in the positive theta2 direction. Okay, so what would be the impedance or the torque acting on J1? So because of that, try to imagine we would see, because of the spring linkage, the torsional spring linkage, the movement of J2 in the positive theta 2 direction will also push J1 or rotate J1 in the same direction. So here we would have arrow in the clockwise direction. Okay, and the magnitude is given by K, or the impedance given by K times theta 2 of S. So that's figure B, and figure C is combining and collecting all of the factors, factors being theta 1 and theta 2 in a single figure. So we will arrive at figure C. So we continue the same steps. We continue with the same steps for J2. Again, for figure 1, assume that only J2 is rotating in the positive theta 2 direction. So there's no external torque acting on J2. So there's no T in this figure. However, we would see the impedances acting on J2. So first impedance from the initial factor J2 S squared theta 2 of S, then the damper opposing to that particular motion D2 S theta 2 of S, and finally the spring component, and the impedance is given by K theta 2 of S. Figure B for J2, we have to write the schematic for the torques acting on J2 only due to motion of J1. So now try to imagine in our head, J2 is stationary, J1 is rotating in the positive theta 1 direction, and because of that, there's a certain torque that will be translated through the spring, and the impedance is given by K theta 1 of S. And basically figure C is combining and collecting all of the factors into a single schematic, which we will then arrive at this particular figure. So that is the first step, drawing the schematic. In the next step, from the schematic, we have to write the equations. So for a 2 degree of freedom mechanical rotational system, these are the two equations. So let's write them out. So the first term is the sum of the impedances connected to the motion at theta 1. So we refer to the first schematic, to the first figure. So the first impedance, so let's sum them up into the equation. So we would have, okay, so we would have the first component here. So that would be J1 S squared. Okay, so that's theta 1 of S. Okay, so that's the first one, plus we would, so that's this one. The second one is from the damper, so we have D1 S theta 1 of S. Okay, the second one. The third one is this one from the spring, so we have plus K theta 1 of S. So just collect all of this term. So this is actually J1 S squared plus D1 S plus K, and the whole thing is actually multiplied with theta 1 of S. Okay, so that is the first thing over here. Next, we have to minus the sum of the impedances between theta 1 and theta 2. So look at the first figure here. So we only have this term from contributing to the equation from theta 2. So here we have minus the sum of impedances for this one is just K. Okay, there's only a single term, and this would be K, this has to be multiplied with K theta 2 of S, and this would be the sum of the applied forces, or torque, actually it should be torque for at theta 1. So here we would have the torque is T of S, okay, which is this one. So that is the first equation. Second equation, going to the next row, we would have minus sum of the dependencies between theta 1 and theta 2. So refer to the second figure now. Okay, so here we would have minus. So what are the terms that has the theta 1 as in it? So we only see one, which is this one. Okay, so we have minus k theta 1 of s. So that's this one. And the next term is this one. We have to add the impedances connected to the motion at theta 2. So here we would have plus, okay, so there are 3 terms, this one, and also this one. So let's add them up. So we have j2 s squared plus d2s plus k, and this whole thing will be multiplied with theta 2 of s, and this is equal to the torque applied at theta 2, and in this case this is just 0. So this is our second equation. And we can again, similar to mechanical system, we can actually write equation 1 and equation 2 in terms of a matrix. So writing this in terms of matrix operation, we can actually write this matrix equation. So the first matrix is a 2 by 2 matrix. The values are j1 s squared plus d1 s plus k. Okay, the value in the second column is minus k. Okay, and the first matrix will be multiplied with theta 1 of s as the first row in the first row, and in the second row we have theta 2 of s. Okay, and this will be equal to another 2 by 1 matrix. So translating the equations, the two equations that we obtained previously, the first value in this particular matrix is t of s. So that's the first equation, and the second equation is just transferring the two equations previously in the matrix form, and the last value here is just j2 s squared plus ds as d2s plus k. Okay, and the last value is just 0. So this is the same equation written in matrix form. So to simplify, or just denoting that the 2 by 2 matrix is the A matrix, so delta in this case is the determinant of matrix A. Okay, so if you remember, finding the determinant AD minus BC for matrix A, this would give us delta to be, so just for the sake of completeness, so I'm just going to write here j1s squared plus d1s plus k. Okay, and this is multiplied with j2s squared plus d2s plus k, okay, minus k squared. So that is delta, our delta. And again, in order to arrive to the final solution, we are asked to find the transfer function theta 2 with respect to ts. So again, using Cramer's rule to solve two simultaneous equation, okay, we will then write theta 2 of s to be the determinant of a modified A matrix. Okay, so since theta 2 is the in the second row in the second matrix, so the first column would be the same as the first column in matrix A. So we have j1 s squared plus d1s plus k, and the second column at the second row, the first column in the second row is the same. And for the second column, we replace whatever on the right hand side. So here we would have T of S in the first row and 0 in the second row. Okay, determinant of that matrix divided by delta. So if we work this out, this would be on the numerator we would have 0 minus T of S times minus K, okay, over delta, which is equal to K T of S over delta. And finally, our final solution, G of S, which is theta 2 of S over T of S, is just K over delta. So that is the solution for this particular example.